What's up, guys? In this video I'm continuing on with the machine learning coding series, and in this one I'll be covering DALL-E Mini. So that's the open source implementation of the OpenAI's DALL-E model. And when I actually say I'll be covering DALL-E Mini, what I mean, I'll be covering this minimal port of DALL-E Mini that's inference only, and that's basically written in PyTorch. And the reason is it's much easier to go through this one and to set it up on my Windows machine. So we'll start with this one, but in the next video I'll actually be covering the original JAX code base of DALL-E Mini, which is much more involved. But this video will give you enough context to know what's going on. Okay, so as usually, I'll first give you the additional context in the form of explaining the papers behind this. And one thing that's very important to understand is that DALL-E Mini is not actually an implementation of DALL-E model. It's more of a mixture, and let me open up my OneNote. So it's more of a mixture of this paper called VQ-GANs, or Taming Transformers for High Resolution Image Synthesis. So that's the paper that introduced the VQ-GANs. And I've covered this one and all of these papers actually pretty much in my previous videos. So I'll be linking those as we go along. So this is the VQ-GAN paper, and they also leverage this model, which is an encoder, decoder, transformer model called BART, and they use some modification of BART. They use this glue from Noam Shazier. We'll see all of those details a bit later. And here is the original DALL-E paper, and then I'm gonna kind of contrast what DALL-E Mini is with the actual DALL-E paper. They also have weights and biases also have a report, which will literally skim through. I'm going to show you some of they actually have very nice training and inference diagrams here, how DALL-E Mini works. And they also have comparisons between DALL-E and DALL-E Mini, and you can see there is quite a lot of bullet points here. So I'm going to go through all of those a bit later. Okay, so let's first start with actual papers. I'm gonna literally just give you the gists, because otherwise there's like 4 papers that would take too much time. So let me go straight to it. So this is the VQ-GAN paper, and as I said, I previously already covered it. So if you want a deep dive, go ahead and check it out. I'm gonna link it somewhere here. Okay, guys. So again, on a high level, keeping it high level because I've covered this in great depth in a separate video. We have 2 components of VQ-GAN basically. One is the learning the visual codebook here, and that's this component here. And then the second part is after you learn the visual codebook, then you basically train a transformer model to autoregressively model the latent space of visual vectors here. So this is the transformer part. So basically, as I said, we have the first part here, and we have the transformer part here. So how this is trained is very similar to VQ-VAE. Again, that's a paper I've covered before. And a couple of differences are that they are using this thing called reconstruction loss. And the second thing is they're using discriminator here. So basically adversarial approach. And because of that, the images from VQ-GAN are much crispier compared to what you get using VQ-VAEs, which is something that actually DALL-E version 1 was using. Quickly running through the pipeline here, what you do is you feed an image here, you then encode it into a lower dimensional latent space here. So you end up with some vectors, as you can tell here. And then what you do is you kind of snap them onto the closest visual vector that you learn in this codebook. So you can see that, for example, for this vector here, the closest vector as you can see here, L2, by using the L2 as the definition of closeness, you snap it onto vector number 1. So that means this one was closest to this vector number 1 from the visual codebook. Okay. So once you do that for all of the vectors from your low dimensional space here, you snap them onto discrete vectors here, then you pass them through a convolutional decoder to get the image out. And then again, I'm going to show you the losses in a second, but you train them using a couple of losses such as the reconstruction loss, the perceptual loss, and the adversarial loss here. And then the transformer part is, I guess, very self-explanatory. Once you have this whole pathway here that allows you to map your data set of images into a data set of basically tokens, because you can flatten out this in a raster order, and you end up with, you can directly map your image into a sequence of tokens, then you basically can just train your transformer on this new data set of basically sequences. And that's how you learn how to, well, the data distribution of interest. Okay, so that's it on a high level. Here are a couple of formulas I'm going to show you. So basically, as I said, what you do is you snap your vectors. So basically, and I have some glitch with my OneNote, so you can see, you'll be seeing this thing kind of staying here, unfortunately. But yeah, for whatever reason, OneNote is glitching today. So here is the vector that you estimate, then you snap it onto the closest codebook vector here. That's the quantization step here. So you first encode it, then you quantize it, and then you have the basically decoder part. And that's how you get the reconstructed image x hat out. And with that notation under our belt, here is the actual loss. The VQ loss is just, as you can see here, a sum of a couple of losses. One of them is reconstruction loss, which is L2 in this case here. And then there are a couple of these losses, which I think they call commitment loss, this one. So the idea, as you can see here, is you put a stop gradient in this particular case here on top of your codebook vector, and then you try and make sure to make your vectors closer to the codebook. And here is the opposite. Here you kind of put a stop gradient operator on top of your estimated vectors, and then you try and make your codebook closer to the output of your encoder, as you can see here. So that's that. And then the VQ-GAN actually adds a couple of modifications. So first one is they replace the L2 loss, as you can see here, for the perceptual loss. And they introduce an adversarial training procedure as well with a patch-based discriminator. So you don't have a single scalar. You have, as you could see on the image here, you actually have basically you're doing a patch-based discrimination of whether that patch is real or false, stemming from real or false image, and that helps additionally. That kind of increases the bandwidth of the learning signal compared to just using a classical scalar. Okay, and that's pretty much it. That's what VQ-GAN changes. So we have the VQ component, and then we have now the GAN component. And again, the difference here is that they are using the perceptual loss. If you're not familiar with what that is, check out some of my neural style transfer videos. But basically, the idea is to take like a pre-trained convolutional neural network, such as like a maybe VGG pre-train on like ImageNet or something, and then you, instead of doing the L2 in the pixel space of your reconstructed image, you actually feed it inside of that network, and then you do L2 in the latent space of that network, where the features are much more abstract, and you're basically trying to find well, you're basically capturing the semantics much more than high-level noise in the picture space. Again, refer to my video if you want to know more details, but this will be enough, more than enough for the code walkthrough. Okay, guys, so let me show you one more thing in this paper, and that's conditional synthesis. So they mention it here. So if the conditioning information C has spatial extent, we first learn in other VQ-GAN to obtain again an index-based representation, as you can see here. So you'll have what they say here, they'll have a height times width of these vectors, where the set of vectors is this big. There is like big Z sub C number of those vectors. So that's the size of the codebook for that conditional information. So they're let me give you a concrete example here. This could be maybe like semantic segmentation maps that you can then basically learn a VQ-GAN on top of that type of a data set. Okay, blah blah blah, and then you have this newly obtained codebook, and then due to autoregressive structure of the transformer, we can then simply prepend R to S, which is the well, that's your image from your target data set, and R stems from the conditioning information. and then basically you do the negative log likelihood to these entries. So in case that was not that clear, let me quickly draw it here. So again, imagine you have basically some semantic segmentation masks here. So maybe something like this. I'm gonna kind of try and draw it somehow. So this is some type of a semantic segmentation image, and you have a big data set of such images. And then what you do is basically train a VQ-GAN such that you'll end up with a particular codebook for that vector, for that data set. So this is going to be your codebook for this particular image here. So you then encode it. You end up with basically, well, you end up with HC times WC vectors. You then flatten them out, and you end up with a sequence. And this sequence, which they denote as R, is something you can prepend while training on your data set. Okay, so now obviously for each of these images, you have an actual image you care about, which is the image from the data set you're trying to, for which you're trying to learn the data distribution of. So that will be some image here, which is actually original image, and this is its semantic segmentation. And then you do the same thing here. So you first learn the VQ-GAN component. So something like this, and I'm really terrible at drawing today. And then you encode it here. You flatten out this sequence. I'm gonna denote it with a different color. So we now have a sequence here. And now how you're gonna train is you're gonna prepend this vector R. So you'll grab the vector R from the semantic segmentation map. And here you have the target image, which they denote as S. And now you just collect these tuples for your whole data set. So you basically collect this, and then you learn how to model that type of sequence. And so how do you, later when you want to generate a new image, you literally grab an arbitrary semantic segmentation map, and you pass it through the encoder here. You fetch this vector R, and then you put it inside of your transformer. So here you'll have a transformer. You put the R here, and then you autoregressively keep on generating the sequence, and then you pass that through the decoder here. So once you generate that sequence here, you pass it through the decoder, and out comes the image. So this will maybe be in practice like 256 tokens, which you can then rearrange into 16 by 16 tokens, something like this. And then that's the low dimensional representation. And then you kind of, as I said, you pass it through the decoder and you get your image out. So why I took some time to explain this is because DALL-E and DALL-E Mini use a very similar approach. Instead of using the semantic segmentation masks, they're actually using text. But the logic is super similar. So just instead of doing this whole thing, you pass a piece of text that's associated with your image here, and then you learn how to model them together, and that's it. So literally by doing that, you learn the data distribution P, X, Y. And that's where the BART paper comes into picture. So that's where this paper comes into play. I'm gonna explain to you, I'm gonna explain to you in a second. Like it's a very simple, it's basically like an encoder decoder transformer. There is not too much to say there. Okay, so again, how BART will come into play here is instead of doing this pipeline with semantic segmentation masks, you'll instead have an image, and you'll have associated caption here. So some piece of text here. Okay, so you'll have some piece of text here, and you'll basically feed that text through encoder part of BART. So let me kind of denote the BART such as this. Like we have encoder part of BART, then we have the decoder part of BART. Decoder is obviously attending the encoder part. That's how the transformers work. And so you grab this text here, you basically feed it directly into the encoder part, and out comes something from the decoder. Out comes this thing here. And now you use this output of the encoder as R, and that's it. And now you just, again, you'll now have these tuples of these conditioning vectors and your images from your data set, and you just learn how to model the P, X, Y. So the distribution of your images and captions. And by the way, this is literally these two boxes is everything you need to have. Like, that's a mental model of BART I have when I'm discussing it. So the only thing we need to see to understand how BART works compared to all of the other transformers is, I guess, this thing here. So basically, in your regular, for example, in BERT model, so in BERT, what the pre-training objective looked like is you masked out. So it's bidirectional. So it's only encoder part of the encoder decoder original transformer structure, whereas BART is both encoder as well as decoder. So you're trying to just kind of mask out certain tokens, and I think like you do that with like 10-20% probability for each of the tokens, and then you try to predict what the token at that particular position was. So it's a simple like a autoencoding objective. And what's different with BART is you can kind of take a span of tokens and then mask them out with a single mask token, and then make sure to predict the original sequence here. So because of this thing, you can mask it out here however many tokens you want, and then predict them here, you have additional flexibility which you don't have with a pure encoder like transformers such as BERT. And I think they mentioned it somewhere here. Let me find that piece of text. So the objective is called text infilling, and they mentioned here a number of text spans are sampled with span lengths drawn from a Poisson distribution with lambda parameter equals 3, and each span is replaced with a single mask token. Zero length spans correspond to the insertion of mask tokens. And okay, it's inspired, blah, blah, blah. So text infilling teaches the model to predict how many tokens are missing from a span. And that's all. Like, it's literally an encoder-decoder transformer with this particular denoising objective. And they show a bit later here how it compares against the baselines using different types of like pre-training objectives, such as just token masking a la BERT, or token deletion, or text infilling, so a bunch of different sentence shuffling, document rotation, etc., etc. And they compare that against the language model, so that's just predicting the next token, or masked language models such as BERT, etc., etc. And they show, well, competitive results. Okay, that's the BERT part, the BART part. And then there's a small modification called GLUE, which I'll show you a bit later. So GLUE variance improved transformer from this author, Noam Shazier, who is actually the co-author of the original transformer paper. So he's a very prolific author. But before that, let me just quickly skim over DALL-E version 1, which came from the paper Zero Shot Text Image Generation. Again, super similar pipeline to VQ-GAN. Again, they mentioned here they have two stages. So in the first stage, they say here, we train a discrete variational autoencoder to compress each of the 256 RGB images into 32 by 32 grid of image tokens, each elements of which can assume 8,192 possible values. So that means that the codebook size is this big. And this reduces the context size of the transformer by a factor of 192 without a large degradation in visual quality. Because if you divide basically 256 times 256 times 3, because you have RGB image, into 32 times 32, you end up with 192. Okay, and the same authors of this paper. Well, I think this is from OpenAI. So basically, they previously trained this model called Image GPT, and in that model, they were autoregressively learning how to model the images in the pixel space, which is much more complex because transformers have quadratic complexity, and obviously the image space can grow like up to like well, 1,000 by 1,000 images, and so it becomes very quickly impossible to model in the pixel space. So that's why this reduction, this mapping into a lower dimensional space here. Okay, so again, that's stage one. And it's literally the same as VQ-GAN without the perceptual loss and without the adversarial component. And then they say here in stage two, we concatenate up to 256 BPE byte pair encoding text tokens with the 32 times 32 image tokens that come from the stage one, and train an autoregressive transformer to model the joint distribution over text and image tokens. So basically what I said here is that, so again, they train the VQ-VAE, which you can think as same as VQ-GAN. So they have the encoder part, they have the decoder part. They kind of have a low dimensional representation here. And so what they do instead, so they can kind of unroll this in a raster order to end up with a sequence of tokens S. So to get R, so to get the conditioning vector, and I don't know why they're using R, like I guess C makes more sense, but I'll just keep on using the same terminology. So to get the R component that you'll use to prepend here and then autoregressively train a transformer on top of it, they just use, as you saw here, they just have basically they take a piece of text and they BPE encode it. So you start with the text and then you apply the tokenizer, which gives you a sequence of tokens. It just gives you a sequence of tokens, and then I assume they just embed those using like a shallow, like a simple, well, you have an embedding table, you map that into tokens, and then you place that directly here to start modeling. Whereas, as you saw, DALL-E Mini is using BART encoder. So that means they'll have additional layers of processing before they output this R vector, so the conditioning vector. Okay guys, that's pretty much it. Let me quickly show you what they say here. There is a lot of complexity hidden in here. As I said, I covered this one, DALL-E one, in a separate video, so you can check it out. They use stuff such as Gumbel, softmax, relaxation to train this model, etc., etc. And also it's worth keeping in mind, I think they mentioned it somewhere here. Let me just show you this. So getting the model to train in 16-bit precision past 1 billion parameters without diverging was the most challenging part of this project. So training this big model, well, back a couple of years ago, this was considered a big model, was extremely hard, and that's something I think Boris, the main developer of the DALL-E Mini project, is also struggling with. But he's using JAX, and he has like free TPUs from Google, so that kind of helps because TPUs have, they did mention somewhere here that TPUs have some less problems than GPUs in certain aspects. Let me quickly show you one more thing. Again, let me just explain this conditioning part. So given a text image pair, we BPE encode with lowercase captions using at most 256 tokens with vocab size 16,384, and encode the image using 32 times 32 tokens with vocab size 8,192. The image tokens are obtained using argmax sampling from the VAE encoder logits without adding any gumble noise. Finally, the text and image tokens are concatenated and modeled autoregressively as a single stream of data. So that's something we saw multiple times already. Okay guys, so that's it. It's a very simple model, as you saw here. There is a lot of overlap between the ideas between VQ-GAN paper and DALL-E version 1. They took the ideas from BART, they took some other ideas. Boris is experimenting a lot. As soon as a new paper comes out, such as the DeepNet paper with novel initializations, he tries an experiment with it. Okay, so let me now show you the report that Boris wrote with the other co-authors. Again, they have a very nice drawing of the training pipeline of DALL-E Mini model. As you can see here, again, they have the BART encoder. So as you can see, you first have these tuples of images and associated captions. Then you pass the caption through the BART encoder. You get the conditioning vector here. You take the image, you pass it through the VQ-GAN encoder, you get the image tokens, you feed them here. So you can see here VQ-GAN tokens. And then you pass all of that through a BART decoder, and you learn how to autoregressively model these sequences. Simple stuff. As for the inference, we can see it here. So you grab a piece of text, you pass it through the BART encoder, you feed it into the decoder, and then you autoregressively generate the image tokens. You can generate multiple series of these image tokens because the process of generation is inherently stochastic. Then you pass all of those through the VQ-GAN decoder. You get some associated images. So the token sequence from the low dimensional embedding space is projected into the image in the pixel space. And then you can use something like clip to filter out the best images. So you again feed the same caption to clip, and it finds the image that is best described by this particular caption. You can see in this particular example, white snow covered mountain under blue sky during daytime. Clip found that this image here is the best best described by this particular caption. Okay, that's it. Let me quickly walk you through, and I encourage you to check out the whole report in this awesome weights and biases report. But let me show you some differences that the authors of the DALL-E mini model themselves mentioned. So we are grateful for the research and pre-trained models published by OpenAI, which were essentially in building our model. Not all the details on DALL-E are public knowledge, but here are what we consider to be the main differences. So DALL-E uses a 12 billion parameter version of GPT-3. In comparison, our model is 27 times smaller with about 0.4 billion parameters. Now, this report was written a while ago, and so this was the DALL-E mini. Like they now have DALL-E mega as well. And also, I think there is a mistake here because I'm fairly sure the original DALL-E paper used GPT-2, not GPT-3, which are fairly similar, but still. Then they say we heavily leverage pre-trained models such as VQ-GAN, BART encoder, and CLIP. We mentioned all of those so far. And while OpenAI had to train all their models from scratch, our model architecture takes into account pre-trained models available and their efficiency. DALL-E encodes images using a larger number of tokens. So they use 32 times 32, whereas the DALL-E mini uses 16 by 16 from a smaller vocab. And DALL-E uses a VQ-VAE while we use a VQ-GAN. Okay, then they say DALL-E encodes text using fewer tokens, at most 256, whereas where DALL-E mini uses 1024. And DALL-E reads text and images as a single stream of data, while we split them between these BART encoder and decoder. This also lets us use independent vocab for text and images. DALL-E reads the text through an autoregressive model while we use a bidirectional encoder. Okay, so I made a small mistake when I was explaining how DALL-E V1 works. I'm gonna show you what I mean by that in a second, but let me finish here. So DALL-E was trained on 250 million pairs of image and text, while we used only 15 million pairs. Okay, so the difference is scale, obviously the model scale, the dataset scale, etc., but also a lot of difference in the architecture and the training method. Like they don't have the Gumbel softmax, they don't have the VQ-VAE, they're using VQ-GAN, they're using BART instead of using GPT, etc. So DALL-E mini is well, not really DALL-E model. It's a mixture of VQ-GANs and BART and everything else. So yeah, but still, and that's why they are now called Craiyon, not DALL-E mini. But in any case, let me quickly go back to notebook and then we're jumping to code. So I think I mentioned somewhere here that they BPE encode text, and then they just learn how to autoregressively model that. And well, I kind of did correctly explain it, but not quite. So what they do is, so let me just draw this again here. So we have the conditioning part and we have the target sequence. So what they do, how they learn this is they feed all of these into the transformer, and then you learn how to predict all of the tokens. So basically here, so yeah, again, as a target, you just take this same sequence and you shift it leftwards by one step. and that's what you're trying to predict. So this is what you're trying to predict, and then here ultimately you have the end of image token in this particular case, because in this particular example the green part are the image tokens from the VQ-VAE portion. Okay, so that's it. The main thing I want to stress here is that the embeddings for the conditioning part are not shallow. They're using deep transformer layers. Because as you know, like the transformer works by cross-attending previous tokens here, so it will be attending to deeper representations of this particular text here. Okay, guys, there was a bit more than I wanted to to give you when it comes to context and paper overviews, but it is what it is. Let's now dig into the actual code. Okay, so here we are in my VS Code. I'm gonna open up I'm gonna hit debug here, and we're gonna slowly start stepping over the code. Again, I'm gonna skip all of the unnecessary details. I just wanna show you the similarity between what we just saw theoretically and the actual code implementation. Again, this I'm showing you the code from a min-dalle repo, and they only have the inference portion of the pipeline, and it's a port into PyTorch. And it's whereas the original repo was written in JAX. We have some arguments here, as you can see. So I'm using the mega version and not the mini version. FP16 set to false, so that we have higher quality images, but the footprint will be bigger. So I have a 8 GB TPU, and otherwise you'll have problems executing this thing. So let me show you. We'll see how the GPU memory is slowly increasing as we're going through the code. There's a couple of optimization in the code as well, such as soon as the encoder is created and the image is encoded, they dispose of the encoder. So that's controlled by this parameter. Let me see whether they have it here. I don't think it's in here. They have a parameter that literally controls that behavior. Okay, so again, we're using mega. We have a piece of text. I just inputted a random caption here, a photo of a funny dog. Let's see what we get. There is some seed. There is a grid size. We're just generating a single image. Top K for top K sampling is set to 256. Image path. So this is going to be directly dumped into the root of this repo. So the image will be saved there. The models are already downloaded into this pre-trained. I went ahead and downloaded them beforehand so that we don't have to wait. And again, as I said, we're using FP16. So let's continue here. So first off, we're gonna create this min-dalle model, and then we are gonna do this generation process. So let's see what happens here. So again, is reusable is set to false. That's the parameter that's gonna control that optimization behavior. We'll see that in a second. So let me continue here. So here it is, nothing fancy there, just storing these variables. We have number of text tokens that's gonna specify the maximal size of the caption. Number of layers is gonna be 24 for mega. As you can see, the difference between mega and mini is just in the number of layers, number of attention heads, also the size of the embedding space, the size of the glue embedding space. Once we get there, I'll briefly show you the paper as well for glue, and then the text vocab count and the image vocab count kind of differ between these two models. In any case, we just form the paths here for the by DALL-E here, they are literally referring to the BART part of the DALL-E model, so that's kind of potentially confusing. Okay, so basically I'm gonna skip over all of this. We have a vocab JSON and merges text, so that's gonna basically be used to form the tokenizer, the text tokenizer. Okay, and now we just form some paths which contain the pre-trained model's weights. And now we hit initialize tokenizer. Let me just see what I have. Yep, I have a breakpoint here. So basically it's already downloaded, so we can ignore all of this. And now we just open the vocab, and here it is. So let's see what's the size of the vocab. So length of the vocab is 50,265. Now we go and read this merges file that contains basically all of the merges that happened during the training of the BPE tokenizer. Do check out my OpenAI clip video if you're confused by the tokenizer details. I've covered that there in a bit greater depth. So let's continue here. We just stored the vocab we loaded a couple of seconds ago. We basically grabbed the pairs from this merges object, and we split them into tuples to get the pairs. So let me show you an example of what the pair look like. So pairs, and I'm gonna print the first 3 pairs. You can see I and N characters are merged together. And this weird, I don't know how to pronounce this one, etc., etc. So there's going to be a lot of those BPE merges stored in the pairs. This rank from pair is basically going to associate integer from 0 to the length of pairs with each of the pairs, and that's going to be used during the tokenization step. I'm going to quickly later show you how the tokenization works on a very high level, but I'm going to skip this part here because it's fairly intricate to describe, and you can read on BPE yourself. We can just treat the tokenizer as a black box. That's fairly common structure between all of these models, so I'm not gonna keep on explaining it every single time. I did cover it in an OpenAI's clip video. Okay, so continuing on, because the is reusable flag is set, we're not going to beforehand create encoder, decoder, and detokenizer, which is the VQ-GAN decoder, because otherwise the memory would literally explode. So I don't have enough memory on my machine to do that. So we're gonna skip over that, and now we have the generate image part. Okay, so we have the model here, and let's now generate the image. Again, the encoder and everything else will now be built on the fly. So we have the text again, we have the photo of a funny dog, blah, 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 same parameters as before. Let's see what this does. So there is this generator function that they developed. That's not that vital. So we're just gonna generate this stream and then doing next, we're gonna grab a single image from this stream, but let's dig into the actual function. Okay, nothing happened there because it's a generator. So once we hit this line, when I go F10, we're gonna enter the actual function. Okay, so similarly here, everything interesting happens in the generate raw stream part. So I'm gonna ignore everything else here. So now let's see what's going on. Okay, so first off, we, depending on the grid size, we estimate the number of images. Because the grid size is 1 for us, we just generate a single image. So this grid, this project offers an option to generate like a grid of multiple images. Here, because of memory constraints, I'm just dealing with single image, so we can ignore the grid every single time. Okay, so because we are in a verbose mode, we are printing out some details here, tokenizing text, etc., etc. And now we hit the tokenization part. So now we tokenize our input caption before we feed it into the BART encoder. So let's see what's going on here. So they grab the separation token, the CLS token, and the unknown token here. There's some processing that they do on top of the text. So they do lowercasing, and then they encode it as ASCII with this error set to ignore, and then they do decoding. So this is just gonna do some simple primitive processing of text. Nothing fancy there. Let me print the text for you here. Let's see what happened. Basically nothing happened with this particular sentence because it was fairly simple. And then you literally kind of split the sentence into words. And splitting is happening, so basically you use spaces to split the sentence into words, and then each of the words is going to be split into the subwords here, because this get byte pair encoding, which I'll skip, it's fairly complex to explain, but it's just going to split the word into BPE subwords, and then each of the subwords is basically associated with the with a specific index integer from the vocab here. And that's it on a high level. And then we just kind of bracket that with a CLS token in the beginning and this separation token at the end. And that's how we form basically a sequence of tokens for our particular text. Okay, then they do optionally here the cropping, but because we are less than 64 tokens, I think this is set to 64. let me see what this number is, but I'm fairly sure it was 64. Yep. So if it's longer than that length, then they crop the tokens. But for us, it's not. Okay, so just some printing because it's verbose mode, blah, blah, blah. Now, as you can see, this is the interesting part. So they create this variable text tokens, which is initialized as all ones. And you can be confused by a couple of details here. So first, why it is ones is because one is a pad token in this vocab. And that's kind of implicit here because this is, as I said, just a port from the original repo. So sometimes things are hard to understand unless you understand what's going on. So here am I trying to explain to you that. So that's one detail. The second important detail is there is this number 2. And why they do that is because they have a basically analog thing to classifier-free guidance that we saw in the Fusion model. So you can basically do the same thing for the class of autoregressive generative models, and that's why they have 2. So as you see here, they create the first sequence will just contain the CLS and the separator token. So it's going to be literally empty sequence. Everything else is going to be paddings. So that's what we do on this line. And then on the second line, we add the actual tokens. Okay. So let me show you what this thing is. So text tokens, if I print text tokens 0, and then first maybe 7 tokens, you can see it's an empty sequence because this is a CLS, this is a separator token, and everything else is padding. And the second one contains the actual tokens for our caption. Okay, that's it. Now we just convert that into tensor with a long data type. We put it onto GPU and we continue on. Okay. Now here's the optimization I was mentioning. Because we're using this not reusable, because we said this flag is reusable to false, we now on the fly initialize the encoder. So the encoder is going to be the VQ-GAN encoder. So let me step inside of here and let's see what's going on. So again, because I already downloaded the model, we can skip over all of these steps. And we're going to focus on how this DALL-E BART encoder is constructed. So the interesting part, as usual, is going to be in the forward pass of the model. And after we construct it, you can see here we just load the parameters of the pre-trained model that was trained in the actual DALL-E mini repository. We're going to load those parameters, and then we're going to push this model onto the GPU. Okay, so let's see how DALL-E BART encoder looks like. Here we are. We have the vocab size of 50K something. We form the embedding tables for the that's the text vocab because encoder, again, remember, has the text vocab, and the decoder will be generating the image token, so it will have a separate image vocab. Okay, so we generate that table. The embedding vectors will be 2048. We then generate the positional encodings here. This is going to be only 64 because if you recall before, we had the cropping so that we make sure that the number of tokens that we feed into the BART encoder is always up to 64, never more than that. And that's why we never need to go above 64 positional encodings. Okay, now we start forming the basically encoder layers, and we'll have 24 of these for the BART encoder for DALL-E Mega. I'm gonna go here and put a small breakpoint in encoder layer, which is a simple transformer block, nothing fancy. The interesting part is this glue, so I'm gonna set one breakpoint there, and that's it. So let's now continue execution here. So we end up in the encoder layer. As you can see, it's just a simple transformer block. We have the encoder, we have the self-attention module, we have the some layer norms, and we have glue, which is just a modification of the your regular MLP that's used, the feed forward like a layer of the transformer block. Okay, so let's see how glue looks like. Here is glue. It's a very simple modification by Noam Shazier, And I'm gonna now open up the paper side by side to show you what this is and to make sense out of it. But it's a very experimental finding, so there is nothing, well, fundamental understanding you can get from this. Okay guys, here it is side by side. Here are the equations from the glue paper by Noam Shazier. And you can see that this layer here implements exactly this line here. So the idea here was they kind of like he ablated a couple of, he made a couple of modifications. Why not using different activation functions? Instead of ReLU, why not using JLU or Swish, etc., etc.? Why not combine them in a bit different ways using similarly to the gated linear units? So you can see, like DALL-E Mini ended up using this variant here. And let me just kind of convince you that that's indeed the case. So let's see. So we get the input X, this is X, and then we pass it through layer norm. So ignoring that part, we then pass it through a linear layer. So that corresponds to basically this bracket here. And after that, we pass it through JLU. So that's this part, the sigma of this. So that's this term. And then we have V, which is formed from X as well, from the input. We also pass it through the linear layer. So that's this part, the X times big V. And finally, we do element-wise product, so Hadamard product here. And then we pass that product through a layer norm, and so that's basically what happened here. And finally we do a feed forward through a linear layer. So that's the W2 here. And thus you can see that this simple forward pass of this glue model implements exactly this FFN glue from Noam Shazier's paper. And that's it. Now let's go back to the code. I'm gonna remove this breakpoint. So it's a simple modification. Instead of having just like a feed forward, basically a linear layer followed by a ReLU followed by a linear layer, it's a bit more intricate. And they showed experimentally that this gives better performance, but there is ultimately no theory behind why this should work. And that's it. That's, I guess, deep learning. Let's continue. I'm gonna now, we're now back into the encoder layer. And again, encoder layer is simply a transformer block. So we have, as you can see here, we have some layer norm and then attention and then norm and then the residual connection, and then we pass through the feed forward part, and then we have again the residual connection, and we return back the variable. So that's it. So I'm gonna basically ignore all of these breakpoints, and let's form the 24 layers of this BART encoder. So I'm gonna hit F5. We're gonna form 24 layers, and then we are now here. We form additional layer norm, and then we form these token indices, which are going to be used to index the positional embeddings here. And that's it. And we just do ×2, because remember, we are doing the classifier free trick for autoregressive models. That's why we have batch size of 2 here. Okay, that's it. That's the initialization of the BART encoder. Now we are loading the weights here, and then we kind of push those weights into the encoder structure, and then we delete the parameters. Now you can already see that this is pushing my GPU somewhat. Well, actually not that much. Okay, so I'm surprised. This is actually not that big of a memory footprint. I think some of the later components will be spiking it up. But yeah, let's continue. So after the initialization of the encoder, let's see what else happens. Okay, and now we grab the text tokens and we pass them through the BART encoder, as we saw in the paper part of the video. Okay, let's step into it. So we're gonna hit the for function of the BART encoder here. So let's see what happens. So we ask where the text tokens are not equal to 1. And 1 is, again, remember, they're not using a constant here. They're just using 1 to represent the pad tokens. So it's kind of hard-coded and dirty, but it works. Okay, so not equal to 1. That's the actual content. That's where attention mask is gonna say true. So let's now do something like this. Let me print this. You'll see that it's basically true for the second component of the text tokens, where we actually pass the caption tokens. We have a bunch of truths here, but for the first one, we only have true for the first two, because those are the CLS and the separator token, okay? Now what we do is we pass those tokens into the, we embed them, and then we just add the positional encodings using the pose tokens indices that were previously constructed. And that's it. That's simple stuff there. And now we just pass it to a layer norm, and then we keep on processing those embeddings via the transformer, BART transformer layers. And that's it. I'm just gonna hit F5 here. We're gonna do a forward pass through the transformer, and we end up with the final representation here called encoder state. Okay, and because again, this is the optimization I was mentioning, we now delete the weights of the encoder. Let's see how the memory footprint is gonna reduce. Okay, so the memory footprint went up. You can see it here. And after we hit delete and empty cache, you're gonna see how it kind of dips down. Hopefully, I'm not sure what's going on. Why is my GPU not reacting here? Not sure. In any case, let's continue. So now we have the initialize decoder part. I'm gonna hit step over, and we enter the init decoder. So again, it's already downloaded, so we don't care about that part. Here we construct it, and again, we'll load the weight. So similar structure as with the encoder. Now we are passing the image vocab, etc., etc. So let's enter the constructor here. So let's see what's the difference. So here we form again the embedding table. This time we have the image vocab size +1, because let me just think here, because they also have they pass this beginning of sentence token, and that's the additional token that they need in addition to the image codebook. So I think they mentioned this somewhere in the report. Let me show you this. So basically, it's called BOS token. Okay, so they say here at inference time, blah blah blah. So a BOS token is fed through the BART decoder, and yeah, that's basically why there is +1. As I said, not the cleanest way to do something, but yeah, this is just a port of the original repo. Now we form the table for the position encodings, and there is only 256 of those, because as you recall from the paper part, the latent space is gonna be 16 times 16 of those basically vectors that are then gonna be fed into the VQ-GAN decoder. Okay, let's continue here. So we now generate a bunch of decoder layers, and decoder layers have additionally the cross attention component, because this is again encoder decoder transformer. So let me see whether it makes sense to kind of show you that part. Let me just think. Okay, I'm gonna put a breakpoint into the init part here, and we can maybe do a single pass here, because they're doing something interesting with this attention state. We'll see that a bit later. And here as well, I'm gonna put the breakpoint here, and now let's continue. Okay, so let's hit the first decoder layer. It's again, simply there is a self-attention part, there is the decoder, there is a cross-attention part, and there is the feed-forward part, so the glue variant in this particular case. So that's pretty much it. So I'm gonna now remove the breakpoint from the init, and let's just generate a bunch of these layers. Oops. Let's now do that. And we do that for 24 times again, I think. Let me just print the layer count, 24. Okay, so there is 24 decoder layers as well. Okay, we have some layer norms, nothing fancy. And finally, we take the final embedding vectors and we map them into the space that has this dimensionality. Because remember, we now want to sample those image tokens. That's why we need to go from 2000 48, which was the internal model dimension, we wanna go into this dimension here. Okay, let's continue on here, and that's it. Okay, that's pretty much it. We load the weights. Again, 24 layers of decoder blocks, and finally then we map into the image vocab size, dimensionality space, output space, so that we can sample from it later. Okay, again, we do the parameters. We put the decoder on top. We push it to my GPU. So let's see whether something changes here. Nope. It's a bit different behavior compared to what I've seen before. Usually there is a spike bigger than this one happening, and I'm tracking this slot here, by the way. Okay, in any case, now comes the interesting part. So here we are going to now start sampling from the decoder those image tokens, and this one is already trained, so everything it samples is going to be meaningful, and then we're just going to pass it through the VQ-GAN decoder, and that's the end of the program. Okay, let's go here. So we're dealing with float 32, so this doesn't make much sense, but with float 16, this kind of puts all of the operations inside of this context in the float 16 regime, which helps us save some memory. So in the case when you have multiple images, this expanded indices makes sense, because you want to replicate the textual captions for multiple images, because you'll be generating multiple images for one particular caption. But we don't care about that here. So we just basically grab the encoder state and the text tokens, and those are of dimensionality. So this is going to be 264 if you recall, and this one is going to be, I guess, 2000 something, 2048, because that's the output of the encoder, right? So 264 2048, because we just embedded this into this dimensionality here. Okay, so we formed the mask again. This is the padding token, so mask is going to be true for the non-pad tokens. We formed this attention state, which is going to contain the keys and values from each of the layers and for each of the positions in the BART decoder. That's just how they decided to implement this. And finally, image tokens is going to contain, that's the output array that's going to contain 256 tokens plus one, because the first one will be the, I think, yeah, the BOS token, the beginning of sentence token. So let's continue. We're going to initialize this vector initially, as you can see here, with this value here, which is going to be the beginning of sentence tokens ID. So let me show you what that looks like. I'm going to take the first 5 elements, and all of them are going to be equal like this. So that's how they initially initialize the image tokens, and then later we're going to keep on, as we produce the image tokens, we're going to feed them back into this image tokens array. Okay, so nothing fancy there. Continuing on, we form these token indices, and we have some settings like temperature set to 1, top K 256, super conditioning factor, which is used for the classifier free guidance part, and that's it. Those are the settings, and now we start iterating basically a for loop 256 times. We're going to generate a novel image vector, and basically then we're going to feed that into the VQ-GAN decoder, as I said multiple times already. So we care about this part of the loop, because this one will enter this one once we have 256 tokens. We'll enter the image grid from tokens function. So let's focus on this part here. So what happens here, as you can see, whatever we take the image, so I is initially 0, which means we initially feed the BOS, so the beginning of sentence token, and we feed the output result into the first slot of this image tokens, and that's how we start populating the image tokens array. Again, its dimensionality is 1 plus 256. It's precisely because of this behavior here. We pass the tokens, we pass the attention mask, the encoder state, the attention state, which is going to contain the keys and values from the decoder, and that's it. And we pass the token indices. So we basically pass where we are in the generation sequence, okay, in the generated sequence. Okay, now let's step inside of the forward function of the BART decoder. So we grab the number of images. We then basically make sure that the batch dimension corresponds to the super conditioning thingy. So it's going to be 2. Okay, so it's going to be 2 there. We grab the list of previous tokens. So previous tokens dimensionality is 1. So that's going to be initially just a BOS token. And then, because we only have a single image, this is just going to replicate the previous tokens. We're going to have 2 BOS tokens, and that's it. Again, the reason being the super conditioning that they're doing. So the classifier free guidance thingy for autoregressive models. Some clamping. I don't think this actually is needed. And then, so now we do the embedding. But remember, this time these are the image embeddings. Okay, so these are the, as you can see here, this is the embedding table. This is a separate vocabulary compared to the text that we use for the BART encoder part. Okay, so we do the encoding, then we add the positional encodings here, and now we have decoder state. It's going to be, I guess, what, 2, 1, 2000 something maybe. Yeah, no, 2048 makes sense. Okay, because we have BOS, a single token, we have 2 because of super conditioning, and we just embedded them into this dimensionality here. So all of that makes sense. Let's continue on here. Now we add the additional dimensions. Now it's going to be 2048. And now we just iterate through the decoder layers of this decoder. So we pass the decoder state, the encoder state, because we have the cross attention, remember. We pass the attention state. So attention state is going to be basically number of layers, and then 4 because we're going to keep keys and values, and times 2 because we have the super conditioning. And then finally we're going to have 256 and 2048. So again, 24 because we have 24 layers, 4 because we are saving key and value for each of the layers, but times 2 because we are using 2 sequences, the one with empty sequence and the one with the actual caption because of super conditioning. And then 256 is because we have 256 image tokens in the decoder, and 2048 because that's the model dimension. Okay, just kind of breaking down the shape is always useful. We pass the attention mask for the input caption, and we pass the token. Now let's hit the for function here. So here we just generate the attention mask depending on where we are in the generation process. So because token index currently is 0, we just have passed the BOS, so the beginning of sentence token. That's why this self attention mask will currently just be active in the 0th slot, and everything else is false. So you can see here that the first will be true, and then everything else is false. And then we just kind of make sure that we have batch dimension of 2 because of super conditioning, and then we just pass the encoder state through the layer normalization, nothing fancy there. And now we pass it through the attention part. So I'm going to skip the attention part. Is fairly well, actually, let me see. This is where we'll store the keys and values. So let me show you this part. So let me just see whether I have okay, so we have a self attention, we have a breakpoint there, so I'm going to hit that breakpoint, and let's see what we do. So we store the keys and values, and let's see what their dimensionality is. So we have 2, 1, 2048, and the same for value vector. We basically concatenate them, and then we store it inside of this attention state, and that's it. And now grabbing from the attention state, we're going to grab all of the previous keys up to this token, which in this particular case is only these keys and values because we are just starting the generation. But that's how the logic is implemented. Using this attention state, we're basically fetching all of the previous keys and values, and that's it. and now we just pass it through we just do the attention logic and we return back here. That's it. Now we have the cross attention part. We pass the decoder and encoder, and that's it. Everything else is standard transformer logic. We pass it now through the glue, and that's a single step through the decoder layer. I'm gonna now remove the breakpoints here. I'm gonna remove the breakpoint here as well. And let's continue on here. I'm gonna hit F5. We went through all of the layers, and now we pass it through again. This final ln is just like layer norm, and finally here is where the mapping happens. So here we're gonna take the vector that's 21,2048, and we're gonna map that into the corresponding into the image space. So basically now the logits will be of 21,16,416 because that's the basically the image space dimensionality. We grab the settings such as top K, temperature, superconditioning vector. Now this part is kind of not completely clear because it's so hard coded. So let me try and break it down. So first we grab all of the along the batch dimension, we grab everything, and that makes sense. We take -1 because we only care about the logits from the last token, because we're trying to sample from there. That makes sense. But this part doesn't make sense. Why is it this number, which is smaller than the number here? And my hypothesis is that, well, it might be that the original VQ-GAN checkpoint they used had a bigger vocab compared to their target fine-tuning after they've done the fine-tuning of VQ-GANs. Not completely clear about this part. In any case, so here's the superconditioning part. So we grab the logits, and as you can see here, we grab the, so these are the logits that correspond to the empty sequence, and these are the logits that correspond to the actual caption. And we do the logic we saw in the diffusion models as well, and that's how we combine the logits to form the final superconditioned distribution here. Okay, so I think, let me just check this. I'm fairly sure. So this is reverse have wings Twitter profile, I think, was the first one to have suggested this type of superconditioning for autoregressive models. So she said you can apply a similar trick to classifier-free guidance to autoregressive transformers to sample from a synthetic superconditioned distribution. Blah blah blah. I trained to try this, and you can see how well basically you trade off the variance with the quality of the images. And finally, this is what we do. So you take the unconditional logits and you just basically add up on top of that this difference times the conditional scale. So this is the same expression we are now using in the code. Okay, let me go back to the code here. So that's basically, if you kind of decompose this, you get that same expression. Now we do some, this is the top K sampling part. So we sort, and we sort in a descending fashion such that the first logit will be the biggest one, and then they start descending. Okay, and then is kept. So we take the original logits and we find basically the 256th biggest logits here, because here's a sorted one, and because we have 256 here, so we're going to grab the 255th biggest logit and use that as a threshold, and all of those logits which are bigger than that threshold are kept. That's how the top K sampling works. Then we do some, this is just for stabilization purposes, temperature, exponentiation, and then we just multiply with this mask. So again, we are just keeping those logits that are basically big enough, where big enough is defined by the top K parameter. Okay. And finally, we just sample from the distribution and we get the image token. Okay, so we now have image token here. That's the token we sampled. And in the next iteration of this loop, basically now we're gonna feed that token as the input, and then we're gonna keep on autoregressively generating the image tokens. So now I'm gonna try and skip all of this. So I'm gonna go and disable all breakpoints. and I'm gonna enable only this one here. I'm gonna hit F5 and I'm gonna let it run until we generate all of the 256 image tokens basically. Okay, here we are. Now let's enter the VQ-GAN decoder. As you can see here, we ignore the first token in the image tokens because that was the BOS, so that was the beginning of sentence token, so we ignore it. So let's jump here. I'm gonna enable all of the breakpoints. Let's see whether I have a breakpoint here. Yes, I do. So let's continue doing this. Okay, here we are. We delete the decoder. That's gonna hopefully release some memory, and we empty the cache. So here, finally, we have this step in memory. This is what I'm used to, and I'm not sure why that didn't happen previously when we were deleting the encoder. Yeah, that was weird. In any case, now we can see it here. Okay, so we now initialize the tokenizer or the VQ-GAN decoder. So let's see whether I have I have a breakpoint there. Again, similar structure as before. We create the tokenizer object and then we just load the parameters. So let's see how it looks like. Again, we pass it the vocab count and the embedding count. So it's gonna have 256 tokens, and this is the vocab count, which corresponds to this is the same size as what the BART decoder had, right? Okay, we form the embedding table, just some processing layers. And decoder, I'm going to ignore how the architecture looks like. It's basically a bunch of like upsampling layers and attention blocks and ResNet blocks. Nothing super, I guess, informative. So we just have ResNet blocks, some attention blocks, which literally do attention, treating image tokens as well, treating images as sequences, and thus we can just apply attention. Just some upsampling. As I said, nothing worth digging deeper into, to be honest. You can go and check it out at your own pace if you want. Okay, so we now load the parameters and we push the tokenizer, the VQ-GAN on the GPU, and now we do the forward pass through the, this is the interesting part. Not that complex, but still interesting. So we have Z. These are 256 tokens, so Z shape is 256. Again, I'm not sure why they're doing the clamping, because we are certain that this will be inside of these boundaries already. So there is some weird thing happening there. That's a consequence of that cropping we saw in with the logits. So that might explain it. Okay, grid size is 1 because, as I said, we're generating just a single image. And now there is a difference whether well, basically the shape of this, how do we feed the image tokens into the actual convolutional decoder part? And we're gonna enter this branch because the seamless is set to false, and we just embed using the embedding table. We embed our tokens, and I assume this is the same embedding table as the one that we had in the BART decoder. That should be shared weights, and now we just do this view thingy, and we end up with 1616,256, and that's precisely the latent space volume that we saw in the papers that we're going to now feed into the VQ-GAN convolutional decoder part. Okay, some permutation, some processing with the CNN. Basically, this is like a single channel CNN. Sorry, the spatial extent of the CNN is 1 times 1. And then we just upsample this image, and we end up finally with Z of shape 256, 256, and 3 channels, and that's our image. And now we do some clipping, renormalization back into the 0 to 255 range, and that's it. Some, again, manipulations on the shape, and let's see what we end up with here. So 256, 256, 3, so that's our RGB image, and that's it, guys. Basically, we now push the image, we convert it into unsigned integer 8-bit format, we push it onto CPU from the CUDA, and we basically convert it into NumPy, and now we basically yield back a PIL image, and that's it. And then we just save the image, and that's it. Now there is also this print ASCII from image function that's very neat actually. So again, ASCII from image makes sense when you're running this from a console. It's just gonna print the image in the ASCII format, I guess. Okay, that's it. Let me step over this, and we are pretty much done. That's the end of the program. Let me now show you the generated image. I should have it somewhere here. Let me open it up, and here it is. So here's the what was our caption? Our caption was a photo of a funny dog, and here is a dog. I'm not sure whether it's funny, but basically that's it. Let me try a different caption, and I'll get back to you once it's run. Maybe like something a bit more complex. This might break the DALL-E mega, but it's worth a shot. A photo of a funny dog, maybe riding a bicycle. Let me run this one, and let's see what we get. Okay guys, here is the actual image. It's kind of weird. You can kind of see it's trying to merge the concept of a dog with the concept of a bicycle, but it's still not that expressive and big to achieve that. So scale is vital for these types of models. And that's it. Do let me know whether you found this video useful. As usually, leave down the comments below if you have any feedback for me. And until next time, bye bye.